Okay, so did you guys try the assignment 2?
I did.
I did. I'm just left with the last one.
Okay, last one. Okay, good. So, so do we have questions? The first one is pretty easy. Anyone has, but that doesn't mean that you don't have questions about that. I don't want to discourage anyone having any questions. Okay. So, any questions about problem 1?
Sir, actually, I didn't start
Sure.
yet, so it would be
Okay.
better if you explained all the questions like the assignment 1 discussion.
Okay. Yeah, I'm not as prepared as I was for assignment 1, but I have a good idea of what's happening here. Okay. So let's just give you an example. So all you need to know about problem 1 is that there is some sort of minimum. Okay. So problem 1, all you need to know is it's something like this. And what you're looking at is just the here. If there's a minima, you're guaranteed a quadratic approximation, right? And then everything else follows from there. You know what the equipartition theorem is for a harmonic oscillator. So there you go. Problem 1 is solved. Okay? You probably you probably like did the derivative, blah, blah, everything. And then you realized at the end that, oh, you didn't need to do all of that. At least that's what happened to me.
I think you do need to in order to prove that there's a quadratic approximation so that you can use the equipartition theorem. Or am I missing something?
Yeah, I mean, all you need to know is that, A and B, if they're generic positive constants, then there will be a minimum, right? For some, I haven't thought about how, if there's a range in which there is no minima, but if there is a minima, then everything else just follows. I mean, if there's a minima by, unless you have a very special value of A and B, the minima would, the expansion of the potential around the minima would be quadratic, right? That would be the leading term. I mean, you can tune the constant in such a way that the leading expansion is not quadratic, but it's quartic, for example, right? But that's just a very, very special case. Do you see what I mean, Saif?
Yeah, you got it.
And then, if you have a harmonic oscillator expansion, then you can use the equipartition theorem, right? So in the next,
I have a problem in question number 7. I did not understand the question 7.
Oh yeah, I'll come to that. Yeah.
Okay.
Okay, let's go to problem 2. And problem 2, the first part, I want you to work it out. There is an integral you have to do. It's a trigonometric integral, and that's it. And the thing that you have to do is that you have to calculate first problem 2. You have to calculate what this is, right? Because E, if this has some theta squared, right? Some constant, some theta squared. And one of the things that you might want to do is that when you apply the when you apply the Boltzmann probability distribution to it, you're going to have like C times theta squared times d theta. Now the integral here goes from some minus theta max to plus max. Oh, there's an e to the power minus c theta squared later, right? So what you can do is that you can, because this thing for values of theta larger than a certain amount, this thing is going to be 0 very rapidly, right? So you can do that to approximate. You can take this integral from minus infinity to plus infinity. And then the result becomes very easy.
Sir, I actually didn't do an integral for problem 2. Like what I did is wrote out the Hamiltonian. So it was quadratic in theta, then there was another momentum term,
Yeah.
angular momentum term, which was also quadratic, and just applied the equipartition theorem for like each of the quadratic parts. We have like half of kt.
Yeah, here the uh, I don't think the kinetic term would be there.
For the harmonic oscillate, I mean pendulum.
Yeah, for a theta squared, because the pendulum is now placed at rest and allowed to come into equilibrium with the surrounding temperature T.
But like, is there? Let's say like we are getting a value for the theta square, an average value which is non-zero.
The average value for theta would be 0.
Yeah. I mean, but for theta square, it's non-zero.
You're right.
So, like, does it not
You still
suppose
have the potential energy.
You still have the potential energy, but you don't have a kinetic energy, right? It's doing some sort of random oscillation, some random vibration. So, Nahi, what you're saying is exactly what I'm saying here. You'll get exactly the same result if you take this approximation, okay? And that's exactly what you did. If you apply equipartition theorem, then you get the result. So yeah, that's fine too. You're using the result that is already derived, right?
Yeah, I'm just using the general form of the equipartition theorem. Probably I didn't.
Yeah, no worries.
Is that okay? Like,
yeah, that's fine. Yeah, that's totally fine. Yeah, okay. So I want you to understand the problem, right? Not like I don't want you to. It's not about, when I was an undergraduate, we had a teacher at Dhaka University who, if you had like, suppose that in your calculation you got to a place where this was like, I don't know, something like this, right? So if you didn't show this as a separate step, he would subtract marks from you, right? So I'm not doing that, okay? This is not, I'm here to kind of make sure that you understand what it's doing. You can do, you see what I mean? Just make sure that you err, at least you explain what you're doing. So yeah, don't worry about it. So let's move to problem 3. Problem 3 has been done in class. So I'm not going to, most of it has been done in class. So I'm not going to dwell on that, okay? Problem 4 is.
I have a question about problem 3, which is
Yes.
that for the rotational one, do we have to derive it again in the assignment, or should we?
Yeah, do it. I mean, that's the whole point. Otherwise, it's like you're just coding lecture notes, right?
Because we did it in the tutorial, so should I just copy paste that?
Well, if you understand it, yeah, sure. If it's in your own words, sure.
Yeah, I wrote it out in the tutorial.
Yeah, of
like
course.
we had to submit the tutorial for
Yeah,
that.
it's fine. Yeah. Sorry, I wasn't thinking when I said that problem. So, but it's good to do a problem again, right? It's free marks for you guys. So problem 4 is trivial, right? Did anyone think it was trivial? You just have to plug in some numbers. And for B, first part of B, you have to argue why you've got the 2n squared factor there, right? We just have to make an argument there. So have you read problem 4?
Yeah, so in problem 4, the energy sketch the energy levels. This is like that standard energy level diagram, right?
Yeah. That you have to work, but the second part is pretty much trivial, right?
Like, so the 2n square factor would come from probably my knowledge of chemistry.
Yeah, which is given up there, right? The degeneracy of
Yeah.
each level is 2n squared. So now problem 5 is a little bit more tricky, but you basically have to show that take the Secor tetrode equation and show that lambda v lambda n gives you lambda s of vn, and show that the expression given in problem 5 doesn't satisfy this. Okay, and that's easy, very easy.
I originally thought that this equation was supposed to be intensive, but I suppose that's not true.
You mean this equation?
The equation that that is given in problem number 5, 3/2 minus log.
No, it's not. It's not intensive.
Yeah, that's where I got stuck.
It's neither intensive nor extensive, right? Yeah. It's just that if you compute the change, then that becomes extensive, because the change, because it cancels out. You see the change in S cancels out. Okay.
Right, I see. Yeah, I got the answer, so that makes sense.
Yeah. So what about problem 6? Did you guys get to do that?
I did that one. I'm not really sure what I'm supposed to get at t equals 0 and t tends to infinity, and I didn't understand the second part of the question.
Sorry?
I didn't understand the second part of the question. M is equal to n up minus n down. I don't even know how to calculate that.
Right. Yeah, I was thinking about that. All you have to do is you can even do it for, so this is actually stolen from Wikipedia. The expression is, what is the magnetic moment, average value of magnetic moment? It's the magnetic moment times the probability that it's spin up, and the probability that it's spin down, right? Now it's very easy from here to translate this to n up and n down, right? Because if you have the total magnetic moment, let's call it, say, I don't know, mu tilde, that's going to be mu times n up, and sorry, okay, what I mean is that if you have n up, then you're basically going to get, okay, what I'm trying to say is that for the total moment, you can relate this to n up, and you can relate this to n down, right? Is that how you did it, Sai?
I didn't do it at all. I was completely confused on that part.
Okay. Anyone else?
Like, I actually did it, but I would like to, like, whether the approach is right or not, I'm not sure. Like, what I did is there was this average energy value that I had to derive in a previous part,
Yeah.
and then what I did is I just I just took, like, the average energy value should be the average number of spin up particles minus the average number of spin down particles times the minus mu p by 2. That's the assumption I use. And
So the average energy is the
n up minus n down,
and then
and
the
average
integral.
of this thing, yeah, this thing averaged
Yeah, times.
times minus mu b by 2.
Should it be 2 by or
In
just
the yeah, it is mu b, but the question gives mu b by 2, so I just followed the question. In the question, it was divided by 2.
right? I see. Okay. Uh,
So like from there, like I just
yeah, I think
took
that. Yeah, I
that
think
expression from the previous
that's
part
that
and
helps.
just
Yeah, yeah. Okay. All right.
okay.
That's a good way of looking at it. Yeah. So, thank you, Nahi.
So in the questions, I feel that like my approaches were quite short. So like, am I like missing something?
What? Which one?
I like for this one, like it's quite straightforward. So like I was thinking, am I
No, I
missing
don't think you're
something, like
missing.
some details that
No, I don't think so.
okay.
No, this is supposed to be an easy question. Not easy, but like you have to think about it, but it's not supposed to be a long derivation or anything. It's more like the conceptual aspect of it.
Sorry, could you explain this statement with the average energy? Why is it true?
Uh, because the difference in this is the difference in the so if you have like one the spin up and spin down state, the difference is in energy is mu b, right? So if you have n spin up particles, then the energy of associated with the spin up particles is going to be mu b, sorry, by 2. Yeah. And if you have n down particles, the energy associated with that would be minus of mu b by 2. And therefore, that this is the total energy. So this is going to be the n up minus n down times mu b by 2, up to some minus sign or something. And then because it's a linear thing, so, okay?
That makes sense. I was thinking I needed to find some expression for n up and n down, but I didn't think about substituting it the other way around.
Yeah, no, it's good. I mean, I think it's a good problem to think about. Okay, so shall we discuss 7?
Sir.
Hello?
Yes, sir.
Okay. So 7 is so you start with the Gibbs expression for the entropy, and then you have to find. Let me just see if I can find the section from David's notes that talks about this. So the idea is that, okay, we have derived, just as you saw in the case of Lagrangian principle of classical mechanics, where you can reformulate Newton's law as an integral principle, right? And even then, you can you go further and reformulate them as a Hamiltonian and stuff like that. So So there's different ways of looking at the same thing that becomes useful in different conditions. So what is happening here is that the canonical, the microcanonical ensemble and the canonical ensemble, these things can be derived from a principle like that. Okay. Sorry, I seem to have lost my assignment. Hang on. Okay. Oh yeah, I found it. Okay, good. So the idea is that you start with the, something. I don't know. Call it. I don't want to call it S. Maybe call it something else. Okay. Some S prime. S prime is S plus some lambda C. Okay. And the idea here is that we are going to. So this S is going to be the expression for entropy given by Gibbs, the Gibbs entropy. Okay. And so S is going to be minus sum over n Pn log of Pn. And then C is going to be a constraint that depends on, what is it we are trying to derive. And we take we extremize S prime with respect to both, say, P of n as well as lambda. So lambda here is known as a Lagrange multiplier. Okay, so if I extremize this expression with respect to lambda, what do I get? I get C equals to 0, right? So that's the constraint that we want to. So, for example, if I take S prime to be S plus lambda KB, say sum over all the sum over all the Pn minus 1. What is this telling me? It's telling me that the Lagrange multiplier is implementing a constraint that the sum of all the probabilities have to be 1, right? Because this is C. C equals to 0 means sum of all the probabilities is 1. So here we don't assume that P has any constraints. So P can be whatever. So that's going to be the equation of S del S prime del lambda 0. This equation is going to give you this. And then we are going to also get S prime del P of n equals to 0. That's going to be another equation. And what we do is that we then use this constraint in this equation, and then we get an expression for Pn. And in this case, it's going to be some constant like this. Sorry, this should be lambda. Yeah, I think this should be lambda. Yeah. So what we're getting here is that the probability is a constant of any state, right? Which is exactly the microcanonical ensemble. So what we are getting is that if we add this constraint gives us the microcanonical ensemble. And what this question is doing is that, I basically did the problem number 1. Problem number 2 is that let's replace this constraint by a different constraint, and that this different constraint is that we have a constant E, bracket of E, which is given by sum over Pn En. And the idea is that, by doing the same thing, you can derive the canonical ensemble, okay? And similarly, you can have more than one Lagrange multiplier, and if you have a Lagrange multiplier which implements this constraint that this is a constant, and another Lagrangian multiplier which says that this is going to be constant, then you can derive the grand canonical ensemble, right? So this is the problem number 7. I think problem number 7 is probably the only one that is slightly challenging. But do you get the idea?
Yes, sir.
Okay. All right, so any other questions?
How come we multiplied the constraint by KB at the top? Just a little bit.
Oh yeah, that's just because you're for dimensional reasons. Because this is otherwise this could be you can change its dimension. That's fine. Yeah. Because this has dimensions of KB, right? And therefore, this as we defined it doesn't have is dimensionless. So lambda has to be a dimension, either has to have dimension of KB or it can be just a number. So I'm just doing it because David did it, but it doesn't have to. He doesn't do it for for the problem, but he did it in the lecture notes. That's why I'm doing it. It's not important.
Also, should the each of the ascending ensembles, if you want to call it that, should they be subject to the constraints of the previous one? Like,
No,
should the canonical
no,
one
they're
have-
completely independent. Yeah, they're completely independent. Okay. Okay, what time is it? It's okay. Let me just. Any more questions?
Yeah, I was going to ask one on number 6,
Yeah.
which was that, like, what am I supposed to expect at the temperature equals to 0, temperature tends to infinity limits? Like, what would make it quote unquote normal or expected?
Sorry, can you repeat the question again?
They said check that your results for both quantities make sense at t equals to 0 and t tends to infinity. But I'm not really sure what they mean by makes sense.
Right. So, I mean, you expect that at t equals to 0, there would be it would be an ordered phase, right? And whereas at t infinity, it would be a completely disordered phase. Right? I mean, I think that's basically what. Hang on 1 second. Let me also check. I think Blundell has a nice section on it. They talk about. They do talk about the Curie temperature at some point. Yeah. So the idea is something like this, right? When you are at very low temperature, but you have an external magnetic field, because there is no thermal noise, thermal fluctuation, all your magnetic moments will align along that magnetic field, right? And therefore, you will have a phase which is extremely ordered, that all the spins would be pointing the same direction. Whereas at very high temperature, there would be sufficient thermal energy and thermal fluctuation such that it would be a completely disordered phase. And your your magnetization would be very small, or would be zero. Okay.
Yeah, that makes sense. They said that in the context of the internal energy and the entropy.
Yeah. What do you think the entropy is going to be for t equals to 0?
0.
Yeah, it would be, and so the entropy would be very high for high temperature, right?
Yeah, I don't know what that means because I graphed my curve and at 0 it's -1.
Sorry.
I don't know what that means for my answer because at 0 temperature it shows that the entropy is -1.
Entropy should not be negative.